Okay, today I'm going to introduce you about quantum principal component analysis. I choose this topic because principal component analysis is a basic machine learning technique. It is used in face, face recognition and many data analyzing tools. So the word only quantum is applied on principal component analysis. So QPCA is a basic quantum machine learning tool. So I hope that you can get an interest about quantum machine learning by listening to my presentation. Second, it's a very famous example of quantum speedup. Uh, Schur's algorithm or Grover's algorithm is a very basic quantum speedup algorithm. And I thought that the next level will be good to study about QPCA. And third, the exact proof of QPCA is not on in Google. There are several formulas in this paper, but there are no exact proofs on the internet. So I thought it will be very good to introduce you about the exact proofs of the formulas in this paper. The paper that I'm going to introduce, it was on Nature Physics, and it has about 7 to 800 quotations. So before we get a look at quantum PCA, we should know what is PCA is. So I'm going to tell you about what is PCA. The main purpose of PCA is shrinking the dimension of the data. We only left the principal component of the data and shrink the data with it, shrink the dimension with it. So how do we shrink the data? We choose some principal components. The principal components will be the axis. As you can see in the picture, there are two axes of these data points. The first axis will make the max variance. We project the data points onto the axis, and if that axis makes the max variance, we call it the first principal component of those data points. Then second, we choose an axis which is perpendicular to the first axis, and if that makes the next max variance, we call it the second principal component. Since the picture is only two dimension, we can get only two axes. But if we have such like high dimension or n dimension, there could be many axes, and we can choose as much principal components we want. So we can shrink the dimension of the data as we want. So let me explain it more mathematically. We will express the data matrix as x. X will be a matrix like this, and the n is the number of the data, and p is the dimension of the data. And we will suppose that the mean of the data is 0, because we can just ship the data points into the origin. So for convenience, we will suppose that the mean of the data is 0. So each data points will be expressed as x1, x2 to xn. And we will say that the axis, the principal component will be the vector w. And we are only interested in the direction, so we will suppose that the norm of the w is 1. As I said, we should make the variance maximum. We will project the data points into the axis, and we will choose the axis which makes the variance max. So we will have a formula like below. We can use the dot product of xi and w because it means projection. Then, since the mean is 0, uh, scaling the xi dot product w will be the variance. So if we add all the xi dot product w square, it will be the variance. And we can write this sigma like W transpose X W. Some of you who had learned linear algebra will know that which W maximize this expression. This expression is maximized when W is the eigenvector of X transpose X. So then the corresponding eigenvalue will be the maximum. I will not tell you the exact proof, but we can choose the ith component, the ith axis, by the ith eigenvalue of X transpose X. And we can choose the corresponding eigenvector as the ith component. So the main idea of principal component analysis is that if we could find the eigenvalues or the eigenvectors of X transpose X, we can find the principal components. So let's think about a quantum algorithm which finds eigenvalues and eigenvectors of a matrix. Most of you will know quantum phase estimation. Quantum phase estimation finds the eigenvalues and the vectors of a unitary matrix. So is it done? We can find the eigenvalues and eigenvectors of X transpose X? Sadly, no, because X transpose X is not unitary. So this paper suggests a way to make the X transpose X into a form that we can use in quantum phase estimation. So since the X transpose X is a density matrix, if we exponentiate the density matrix, it will be a unitary matrix. The terms of unitary matrix and density matrix is in the right bottom. The density matrix will be low and the unitary matrix will be U. So this paper's main proposition is that if we can make the density matrix low into exponential form, we can make it to a unitary matrix. Then we can apply the quantum phase estimation. So let's look how this paper does the density matrix exponentiation. And before we get a look at that, we should have a proposition that if S is a sparse matrix, then we can exponentiate it very easily. Sparse matrix is a matrix that has many zeros. So they said that it is easy to implement and we should just take it. This paper just wrote this formula on the top and didn't have an exact proof of it. So I made the proof into 4 steps, and I hope that you guys can get a look at it. And the formula on the red box is very important because we are going to use it very often. So you should remember the formula in the red box. Then let me explain the expression. The first expression on the left is a partial trace of some expression. A, B is the state of each quantum state, and we will take a partial trace of A, and we will prove that the left expression is same as the right expression. As I said, if S is a sparse matrix, it is easy to implement the exponentiation. So we can make e to the minus I s delta t and e to the I s delta t. Since S is a swap operator and it is sparse. So we can get the left expression in very short time. Let me tell you the proof. Number 1, if t is unitary, the square to the t is I. So we can say that e to the I theta t is I cosine theta plus I t sine theta. If we use that formula into number 2, we can get an expression of this. It's kind of long, but if you just put the number one expression into the number two, we can get this very easily. Then, as I said, we will take a partial trace of it. Each matrix with a tensor product, then a partial trace is wrote in number three. We can say each tensor product, the partial trace of each tensor product is like this. So if we apply the number three expression into number two by taking a partial expression, we can get number four. And finally, we estimate that cosine delta t is 1 and sine delta t is delta t. Then we get the right expression, aka the expression which is in the red box. And as I said, it is very easy. It takes only a third time to make the left expression. And since the right expression and the left expression is the same, it means that we can get the expression in the red box in a very short time. As I said, the expression in the red box is very important. As you can see, it is very similar. The only difference in those two expressions in the red box is that in this expression, we have lobe, and the next expression, we have n lobes. Since we can copy on density matrix as many as we want, we can get this red expression like this, because we deduced this expression in the previous slide. Now I'm going to show that the red expression is the same as the expression on the left. Also, this proof is not on the paper or Google. First, let me tell you the expression number one. In the previous slide, we assumed that t is unitary, but in this paper, the t is a pure density matrix. So the t to the square is same as t. Then by taking a Taylor formula, we can say that e to the I zeta t is same as I minus t plus t e to the I zeta. And number two, as you guys know, density matrix is a sum of pure density matrices. So we can, so if we can exponentiate the pure density matrix, then we just have to multiply all the components of a density matrix. Then if we just multiply, we get the exponentiation of a density matrix. The formula is number four. So we just have to get the exponentiation of a pure density matrix. That is number three. We can write the expression on the left like the expression on the right by using number one. We just apply it and we can get the expression below. Then we can, yeah, just, I'm not going to explain this, but if we put the expressions on this, we can get the expression on the red box. So we have a conclusion that the expression on the left is the same as the expression on the right. So since rho is a density matrix and sigma is an arbitrary unitary matrix, we can get a conclusion that we can implement the expression in the blue box. So this means that we can exponentiate the density matrix as we want. So finally, we can use the quantum phase estimation because we have a unitary matrix that is an exponentiation of a density matrix. I'm going to write quantum phase estimation as QPE, and if we apply the QPE with e to the minus I rho t with those vectors, we can get the vector on, we can get the expression on the right. Xi is the eigenvectors and Ri is the eigenvalue of those vectors. So if we apply the QP, we have the eigenvectors and eigenvalues of the rho. If we just put rho as X transpose F, then we can get the principal components as we want. The ith component has the probability of being measured at Ri, as you can see in the expression. So we can get the principal components by just measuring what we get. Since quantum phase estimation has an exponential speed up, and we didn't use any difficult algorithms, we get the time complexity gets shortened. In the previous just principal components analysis had about d to the square log r plus d r square. But if we use the quantum phase estimation with the density matrix exponentiation, we get QPCA as RD log D. The time complexity is very shortened. Thank you. If you have any questions, you could ask me.
Okay. Thank you for the presentation. I think that presentation was very well organized and mathematically flawless. Okay. So I have a question. So in the previous slide about time complexity, what does large R represent?
The large R is the number of components that we want to get. And D is the number of the data points.
Okay, I see.
Can I have a question?
Of course.
I have a question in 7th slide.
Okay.
Maybe you told S is swap operator, okay?
Yes.
And in proof number 1, if T is unitary, T square is 1.
Yes.
I think the unitary matrix is T times T transpose is 1. Am I right?
Yes. I just wrote it in convenience.
But I think in this case, S is swap operator, so S square is 1.
Yes.
I understand. All right. Oh, okay, thank you. And I have another question at next slide.
Okay.
In last line, e power minus I rho t go to like that. But do you know PCH formula? Baker-Campbell-Hausdorff.
Oh, okay.
Have you heard?
Can you say once more?
Baker-Campbell-Hausdorff formula.
No, I didn't hear of it.
Simply, matrix exponential. If I think e power a plus b.
Yes.
Is not equal to EA times EB. Do you know? Do you heard about that?
Yes.
So I think the line 4 has same problem that in matrix exponential, but how can I ensure that this formula?
I know that if it's a pure density matrix, the formula is okay. And we don't have to get the exact result, because as you can see, we have big O notations and we
Ah,
are just simulating it. So yeah.
I think this is just okay for first order T, I think.
Yes. Yeah.
Okay, good. Matrix exponential can be expanded order by order, like Taylor series.
Yeah. We
In
can do
Baker
that.
has the formula, so it is correct in first order, I think.
Yes.
Oh, okay, thank you. Okay,
Thank
good.
you. Any more questions?
Oh, there is another question. There is another question. Can I have one more question?
Oh, sure.
In slide 9,
9. Okay.
I'm not very familiar with QPE. So can you explain about QPE simply?
It's a tool that if we have an eigenvector, then we can find the eigenvalue in a very short time, but we can use it even if we don't know the eigenvector. You can look, I think I can't explain it in a short time, but it will be good if you look at the HHL algorithm. I wrote it in the chat, and you can
Okay.
look how the quantum phase estimation is applied in that algorithm.
Okay, thank you. Xion uploaded link in chat room. Thank
Okay.
you.